Okay. Once again, good afternoon to all the participants and respected Professor Nand Kishor sir. Today we have experts from MNNIT Allahabad, Professor Nand Kishor sir. Let me introduce his biography. Dr. Kishore has obtained his PhD in 2006 from IIT Roorkee and presently working as a professor in the Department of Electrical Engineering, MNNIT Allahabad. Sir has more than 15 years of teaching and research supervision experience for masters and PhD students. Till date, he has supervised 11 PhD candidates. During 2012 to 13, Dr. Kishore has worked as Marie Curie Experience Researcher, Marie Curie Fellow at Aalto University, Finland for 14 months. He is author and co-author of 69 SCI International Journal publications, out of which 26 number are published in IEEE Transactions and IET Publisher Journals. In addition, two books published by IET UK have been edited by Sir. Some of his recognized research projects includes those of Indo-Norway in year 2015 and 2018 and Indo-Russia 2016. The projects are going on. He has also served as a guest editor on a special issue in the IEEE Transaction in Industrial Informatics. Presently, he serves at subject editor associate editors for two journals, namely IET Generation, Transmission and Distribution and IET Renewable Power Generation, both published by IET UK. Once again, I welcome you, sir, and please, I request you please start your presentation, sir.
Thank you, Dr. Vijay, for my short introduction. I hope I am audible to all, and can I get a confirmation from
Yes,
you, Dr. Vijay, and the
yes,
other
sir, it is
participants?
audible, sir. Audible, sir. Audible.
Oh, fine, thank you. Uh, in fact, in this part of my presentation, because if you refer to the schedule, I have two presentations today. And in the first part, the topics which I have it is disturbance detection in distributed generation system. In fact, during the discussion on these topics, let me clear it out. I will have the discussion mainly related to the work which some of my PhD students have carried out in the recent past. And it is basically their contribution to the research work in the field. And we have been just as a supervisor for them. So main contribution is from my PhD students here. Who have already graduated, right? Now, in the first part, the discussion is related to disturbance detection in a hybrid renewable systems. And this is the topic which I have planned to cover for you. I'm not sure how I will try to have the relevant topics, relevant discussion with your course, right? And let's see that if we have some discussion from the participants also during the presentation. So I would like to have those invitations as well. Moving to the next slide is the introduction to the topic. We say what is the need for the renewable resources and those renewable resources which will be as a small capacity, and they will be located as distributed generations. These are some of the points which we refer what is the need for them. mainly the renewables as a distributed form. And some of these points includes the increased demand for power. Next refers to the shortage of fuels, fossil fuels, and then the cost of the increase in the cost of the fuel, and as well as nowadays we come across the discussion related to the environmental pollution. So these are some of the factors which governs the adoption of renewables, and then it could be as a form of a distributed generations. Uh, in fact, you have come across several presentations in which there has been discussion. So it is almost the same. So mainly the use of wind power, solar photovoltaic, and the fuel cells. They have been, in fact, fuel cell, it is just a smaller proportion, but wind and the solar photovoltaics. So they have in fact gained popularity over the years, in can say over 1 decade, so on. Now, the DG system, they can be in different mode of operation. We can have the distributed generations operation as a off grid, which we call it as sometimes standalone mode of operation, or it could be a case where you have the DG, distributed generation systems, being connected to the utility grid. So thus it can be as a grid connected mode of operation. Now, then there are certain issues in the operation of these DG systems. And here some those it includes operation and control related problem. Because mainly we have the power generation from the wind and solar photovoltaic, and we know very well that the availability of wind speed and in the solar radiation, they are of intermittent in nature. Uh, that is, you say, as you have the variation in the wind speed and the variation in the solar radiation. So they do not remain constant, such that you are able to generate power constant same throughout its operation. So that is not possible. So thus we have a intermittent nature or intermittent characteristics of the power generation, which you get it from renewable resources. With these systems, which are renewable based, there are certain issues in operation, and in fact, though, there are several of them, and some of them are listed here. So first one is the integration part. That means how you integrate, whether it is because the form of the power which is available, it could be as a DC form or the AC form, and that,
Sir,
yes.
sir, participants are requesting that they are not able to visible the slides. So I request you to please again share the screen once
Okay,
again, sir.
okay, okay. All right. Was it that way? Okay. Uh, Now can you see?
Yes, sir, I am. It is visible now, sir.
Now this one?
Yes, sir, introduction.
Okay. So from which part the slide was not available on their screen?
Now they are saying
Okay.
that it is visible, sir. Please go ahead,
Confirm.
sir.
Okay.
Okay, sir.
So do I need to start from the beginning? I mean,
No,
from the
sir,
beginning
just
part? Okay.
please continue,
Okay.
sir. Please continue.
Okay. So as I was discussing that we have the issues related to the integration part, and next one it includes power quality, followed by islanding. And there, in terms of the control, it includes the voltage and frequency here. However, in my part of the discussion for the today's presentation, I will have the topic related to power quality, and islanding issues in the DG system. So I hope my voice is also audible to all the participants. I just wanted to confirm,
Yes, sir,
right?
it is audible, sir.
Thank you. So I move to the next slide here. So in this slide, I like to show, as you can see in the figure, we have the main utility grid, and then you have some another connections to DG here, and then some more connections, and then several DGs here, right? Now, normally the distribution generation systems, they would be operating in parallel. And if in case these DGs gets disconnected, it could be intentional or unintentional. So if that means the disconnection of the DGs from the main utility grid here. All right, so that, but still continuing, because if I refer to this DG here, so you have it connection to the network, bus network, and then again you have also a load. So if in case the DGs which are operating in parallel and in parallel with the main grid, and if due to some reason they get disconnected, but still continue to supply power to the local load demand. So that could be the situation of phenomena or the event which we call it as islanding here. Because of this islanding event occurrence, it could be, as I said, intentional or unintentional. Uh, this event occurrence, it could be hazardous to the workers who are working on the line here somewhere, or the public here, or it may also damage to some equipments if the voltage and the frequency, they are not being regulated by the uh, utilities. And then again, the complexity may arise in the reclosing operation of the DG, and in some cases damage to the DGs in islanding may occur if it is wrongly reconnected to it actually. So that is, we call it as out of phase recloser operation here. So these are some of the implications that we are likely to have because of islanding event occurrence. And thus, next one is the, in this DG system operation is the issues related to the power quality. As per the definition, or we can call it as all possible situation for which the supply waveform, the power signal waveform, either the voltage or the current, the load current, deviates from the theoretical, you can say, the sinusoidal waveform at rated frequency and with amplitude corresponding to the rated RMS value for all the three phases. So that means if there is a deviation in the voltage supply voltage signal from the sinusoidal form, and that deviation is in terms of amplitude uh, corresponding to the RMS value for all these phases. So that could be a situation of related to the power quality problem. And here's I have some of the list. What are the uh, distortion, or you can say the power quality problem can be referred. One could be the sag or the swell in the voltage waveform. Next could be the momentary interruption over, under, or the over voltage or the frequency. Voltage flicker is another form. Harmonic distortion, voltage notching, transient disturbance. And on the right hand side on my slide, I have listed what are the different sources which could lead to power quality issues. And some of them are as power electronic devices, or maybe the nonlinear load, Then some arcing devices, load switching or starting of a large motor, sudden surge, lightning currents, switching of transformer, induction motor, and so on. Right. We move to the next slide here. Now, on this slide, we have the definition for power quality. So, in reference to the voltage signal, this is how we define it. Reduction in the RMS voltage, which could be in the range of zero point 0.1 to zero point 0.9 for a period lasting uh, more than half cycle, and but up to a period up to 1 minute. So if you have a dip, that means sag in the voltage of this range, zero point 0.1 to zero point 0.9 for this much duration, so it will refer in the category of voltage sag, and it is caused by faults. You can have it increased load demand, or there could be also transitional events like large starting of a large motor or a transformer, or that is the energization of a transformer here. uh, Next, very well known power quality issues that we come across is the voltage swell. So, in fact, swell is just the opposite of the sag, and it refers to the increase in the RMS value in the range of 1.1 to 1.8 per unit for a duration uh, greater than half cycle. That is because one cycle is 20 milliseconds, so half cycle to a period up to 1 minute. And again, the swell is also caused by false load switching or capacitor switching here. Uh, and the next one is the voltage interruption. And this is basically the complete loss of electric voltage. And these interruptions can be of short duration, which can be of less than 2 minutes, or it could be for a longer duration in some cases. Uh, Disconnection of electric power, it will result into interruption. Usually, it is by or the operation of circuit breaker, that is the opening of circuit breaker, line recloser, or the fuse. So that way, it may lead to some kind of voltage interruption in the signal. Move to the next slide now. So here, this slide gives you information about my topic for my discussion that I have it here. So what are the different islanding detection techniques? So as I said that islanding can be intentionally or unintentionally. And basically when it is unintentionally, then it is more important to be detected, right? And thus so over the years, in fact, I can say 2 decades, several researchers, they have different way of techniques or the methods reported, right? And they had different form of the techniques reported, actually, I can say. uh, Now, in fact, as per the thus we can have the classification of those techniques here. Now, as I said that islanding, this could be detection of islanding, could be remote technique based or a local technique based. So in the case of remote technique, we use the signal through the communication network, mainly from SCADA. So that means we have the SCADA in the system or the PLCC, and we keep on monitoring the signals at a sample rate, at a definite sample rate from the SCADA and the PLCC, and thus monitor the status of the circuit breaker. So whether the circuit breaker is on or off. So based on the status of the circuit breaker information, we come to know whether the DG is islanded or not. So that is one way. But this is communication based here. Uh, Next one is the in a broad way. It is the local using the local signal information. So that we call it as local techniques. So in this case, we have the access to the measurement of some signals, right? So from the DG location, basically, and it could be like the signals from voltage or the frequency here. Then further, this approach is subcategorized as passive, active, and hybrid techniques. Now, in the case of a passive technique, we have a continuous monitor of these electrical signals, right, to identify the islanding occurrence. So we, that means, monitor the signals continuously at sample rate. So, and that gives you information, that is the decision whether the islanding event has taken place or not. That is one way. In the second approach, we have the active technique. In this case, basically, we try to inject some disturbance into the system, and it could be through the inverter controllers, right? So that means we keep on injecting some disturbance into the inverter controllers and thereby observe the electrical signal characteristic, right? And so as to know whether there is islanding event occurrence or not. And thus, we have the under voltage or over voltage relay, or under or over frequency relay to give you an indication about the islanding event occurrence here. So this is the case where we have to inject some disturbance, and that's why it is referred as active method. Then the last one is the combination of the two, you can say, that is the passive and active techniques here. So this is the broad classification of island detection techniques, and in my part of the discussion, I will have it mainly related to the passive techniques here, where you need to have the continuous monitor of the electrical signals to indicate the occurrence of island event here. Right. Move to the next slide now. And this slide tells you, gives you information about the what are the advantages and disadvantages here, and of these techniques. So as you can see, that remote techniques, they are highly reliable, right? But there are again issues related to expenses, that means the costs, mainly for small systems, because you require the use of the communication network here basically to be implemented. However, if you refer to the local techniques, and then for these sub techniques, you can say, if you include the passive techniques, so they have shorter time detection, and we do not need to perturb the system, because in the case of active, we need to inject a disturbance signal. So here we do not need to perturb, and thus the operating uh, conditions or the operation of the system is not affected here. And this is also accurate when there is a large mismatch in the generation and the demand when the system is islanded. So that is the advantages here. But disadvantage includes it will be difficult to detect when the load and the generation. That means the load power and the generation power, they closely match. They are about same. Then detection might be difficult here. Then in some cases, because we are having a continuous monitor of the signals, all right, and then that means we need to define some threshold, right, some threshold we need to define, we need to design a threshold, a value above which if the event occurs, then it will be referred as, decision will be as islanding. Otherwise, if the value is below threshold, then it will be as a non-islanding event. So that means there has to be some way of designing the threshold value for the system. So that is one disadvantage here. And again, if this setting is too aggressive, then it could result in the nuisance stripping, because uh, If I say that by the too aggressive, it means that if the system characteristics is changing, is highly dynamic. Let's say in one case you have 3 DGs operation and then line and load and so on. But let's say that there is some network configuration change, all right, and then again the or maybe the operating condition has changed, then the threshold which we have designed for the islanding decision, that may result into uh, uh, good bad decision actually, and thus you can say it may have a consequence resulting into the tripping here through the circuit breaker. That is one way. Then active techniques, if you refer, it can have the detection, right? Even when you have a perfect match of power between the generation and the demand, and that we call it as non-detection zone. Actually, this is the NDG word here we use. But the disadvantage includes we need to perturb the system. Detection time is slow because we need to have more time for perturbation. And as I said earlier, that because of the perturbation, it may degrade the power quantity it may have. And again, it may also significantly impact the system stability when it is connected to grid here. That is one consequence you have to bear if you have the active technique, and thus it will be as a disadvantage here. And the last one is the hybrid technique. So in this case, it includes a small NDZ, and perturbation is introduced uh, only when the islanding is suspected, you can say, right? But detection time, as a disadvantage, if you consider detection time is much longer because it includes both techniques here. So this is the brief overview of the advantages and disadvantages of these techniques here. Next, as reference to the passive techniques, I have listed here some of the signal processing techniques which have been in use, which have been applied. And it starts from Fourier transform, short-term Fourier transform, Stockwell transform, wavelet transform, and then again some of the more advanced techniques like empirical mode decomposition, and then again the variants of EMD techniques. We can include orthogonal assemble or energy preserving assemble. So in fact, my work it has been with the use of these techniques here. And as you can see here in the later part of the discussion, so I have some of the results based on these techniques applied. Now, if you recall, if you are ever aware to Fourier transform as a technique for signal processing, it is a fast technique, but its performance is very much limited to stationary signals. Yeah. I will discuss more in detail about what is stationary signals and maybe in the later slides. As an advancement to the Fourier transform, we have the short-term Fourier transform, for which we have a stationary window function, but it requires more computational time here. And thus, next one is Stockwell, which is more time consuming with respect to the other methods. And the last, another technique which I have it here is the wavelet transform. However, its performance will deteriorate in terms of detection capability uh, if you do not have a proper choice of the mother wavelet, right? And also with the presence of noise in the signal, right? The test signal, I mean here. The performance of the wavelet, it may not be reliable. And thus, we can say the wavelet has some, we can say that the deterioration in the performance for island in detection. I have here some discussion on the signal processing techniques to give you about the brief background to the techniques here. And thus, here, as we can see, the Fourier transform. In this case, we represent the signal as in terms of sinusoids, right? And then Fourier transform gives you a signal which is localized only in the frequency domain, and it does not give you any information about the time domain, about information about the signal in the time domain, right? And however, the signals which are of the practical interest and even including the power signals, they are usually non-stationary here, right? And thus, what does this mean? That their time domain and the frequency domain characteristics, they vary over a short time interval. So some of the examples includes like the music, seismic data, or even the power signals. So they are mainly as non-stationary signals here. So what does the stationarity of signal mean here? Uh, Such signals, stationary signals, they have the frequency information uh, constant. So that means over the time period of the analysis, the frequency content, the frequency information will not change here, right? And that means the whatever the frequency information which is present in the signal, it will be available throughout the time period. So if I take this example of a signal variation here, now if you refer, you can say that this signal is actually a superimposition of three different waveform, right? If I see some of smaller frequency, some of medium frequency, and another of much higher frequency here, right? So because if I say take this waveform, right, and then if I take a lower one here, and then if you take this waveform here, so as such, over the time period, this original signal is superimposed to have three different frequency component. So this is the spectrum plot here, right? Right, and this is along this axis you have, let's say, amplitude, and here you have the frequency here. So this original signal is superimposed of one frequency component, which is smaller frequency, then another, let's say it is a medium frequency component, and then here you have a much higher frequency component. And what we observe that during the time period, the frequency component remains as a superposition of only these three frequency component, and thus the signal is stationary here. We call it as stationary signal. Now in contrast to this, we have a non-stationary signal. Now, in the case of non-stationary signal, uh, frequency information changes with time, right? So if you have frequency changing with respect to time, it means that uh, the spectral, the frequency spectral component, they will also be time varying here. And as you can refer on this signal variation as an example, you can see that over the time period, right, over the time period of 1 second, the signal has 5 hertz. Then afterwards, in the later part, it has its signal has a frequency component 25 hertz, and for a later part of the time period, it has much higher frequency component. So what you observe that during this period, time period, the frequency component has changed. And thus, if you look at the spectrum plot, so the signal has a frequency spectrum corresponding to 5 hertz. Then it has a frequency spectrum corresponding to 25 hertz and another component corresponding to 50 hertz here. And thus, uh, for these non-stationary signals, we need to have a perfect knowledge about what frequency component exists here. And but no information about this frequency component you can see they are located in time domain here. So we don't get it here. Thus, the frequency, you can see the frequency changes with time, and is spectral component. They are also changing here. Right, that is the characteristic that we observe in the case of non-stationary signals, and thus some of the signal processing techniques they are not reliable, or you can say the accurate in perfect detection of these frequency or the characteristic information about the signal. Right, we move to the next slide. So here I have a few discussion about the how does the wavelet and the Fourier transform uh, correlate with each other. So if we refer to the case of basic functions that we require for wavelet transform, so they are actually more or less like a small waves but located locally, that means in different time, and they are obtained using scaling and translation. I will have more discussion on this scaling translation in the later slide of scaling function. And thus the wavelet transform is basically localized in both time and in frequency domain here. Now for the analysis purpose, using the wavelet transform, we have the windows of different length. But again, the questions will arise, how to decide what should be the length of here, window length. Now, because if you want to analyze the high frequency component, then you need to have a narrow window so that for better time resolution. And if you want to analyze the low frequency component, then you have to have a larger, a much, you can say, you use a wider window, much larger window for better frequency resolution. So thus, depending upon what you expect about the frequency information present in the original signal. So you may have low frequency component, you may have high frequency component. So depending upon that, you have to select whether a short window or a longer window here using the wavelet transform. And this technique works well if the signal to be analyzed mainly consists of slowly varying characteristics, and which we normally observe short high frequency bursts. So in that case, we have a short time delay, right? And then the characteristics is slowly varying. So in that case, the wavelet transform will work perfectly. Now, this is how we define the wavelet transform. So as per the mathematically, this is the continuous wavelet transform of a signal, which could be X signal here, right? And then using the wavelet function psi. Now, it is a function of tau and s. So tau is the translation parameter, which is basically the time. And next one is the s, which is basically the frequency quantity. And it is expressed as a psi function here. And then we write it in terms of normalization constant here, right? And then which is actually the integral of a signal, that means which is to be analyzed, and the that means the function which is the mother wavelet. So this is how we define the complete continuous wavelet transform here. Now with this slide, I just want to illustrate what we actually meant by the previous discussion. Now, if you refer to this image, on the x-axis we have the time, and on y-axis we have the frequency here. Now, if you consider a longer time length here, longer wave, that means the analytical window length here, right? You are more closer to low frequency component here, right? And if you little bit go up, then you can have, let's say, half time window. You can have half time window, right? And this, there you can have better frequency resolution, but it is possible that you may because you are considering the window length up to this time period. All right, so thus you may miss any event which is after this year or maybe before this year. right? This is one way I can say. And if you go further, so then you can subdivide the time horizon. So if you have, let's say, smaller time period, then you can have a much higher frequency component being analyzed here, right? And if you go further, so you can have a shorter time length. So now I have much shorter time length, and thus you can have a much higher frequency component being analyzed here. So what does this mean? So that means for this complete length of time duration, if I take a signal of 10 millisecond, so you have a signal of 10 milliseconds. So whether you want a low frequency component to be analyzed for 10 millisecond, or you want to analyze for much higher frequency or a medium range frequency component in the 10 millisecond, that we have to decide. Actually, that is our choice. So if you want to consider a much higher frequency component to be analyzed, then in that case, because if you go in this range, so we need to have a shorter time length window. So thus this will give you in fact it will have better time resolution, right? But poor frequency resolution in this part here. And in this part, you have it better frequency resolution, but poor time resolution. So thus it depends upon what information you want to have, whether you are interested in the time instant or you are interested in the frequency component here. But again, for our analysis, remember, we are interested to have both frequency information as well as the time instant, because we want to know the instant the disturbance took place, and with that instant what is the frequency component or the frequency characteristic present in the signal, based on which we will have a decision related to the event diagnosis. So thus it is important here. So but again, it depends upon the choice, whether you want to have a longer time length or a shorter time length, and for which frequency component you want to analyze with the test signal, right? This is I have given you a more clear representation. So if I consider, for example, here a time varying signal, so you have the time domain signal and the frequency component present here, right? So thus it is here, this one, time series signal. Now if you consider the Fourier transform, so Fourier transform for the entire range can have different frequency component being analyzed. So you can do that, right, for the entire range. But if you refer to the short time Fourier transform, then it is possible to divide the complete range into different window length here, right? And then you can have one frequency component, you can have another frequency component being analyzed. That is possible. And if you refer to the wavelet, so depending upon what is the choice you have, you can have a shorter time length here, shorter time length, and but much higher frequency component. And if you can have a longer time length here, as you can see this one, but a different frequency component being analyzed. So you can have different window length for the analysis with the use of wavelet transform. And that is why we say that wavelet transform can give you the signal information in both time domain and as well as in frequency domain here, right? Uh, Next, here I want to give more, as I said in the previous slides. Sorry. So, what is wavelet transform? So, you have an original signal. We have basically the filters here, low pass filters or the high pass filters, which will basically decompose the signal into coefficients like approximate coefficients and the detailed coefficients. This is the mathematical, and if you consider in a graphical form, so we have an original signal which has something 1000 data samples, right? So you feed it to, you have actually as a high pass filter, and then you have as a low pass filter, and thus applying the mother wavelet, you can have detailed coefficients here, And then you can also have approximate coefficient corresponding to low frequency and detailed coefficient corresponding to high frequency component here. So thus you can get a coefficients with 500 samples and here with 500 samples here, that way. Then in fact, depending upon the label that you apply for the wavelet approach. So with this case, you have the original signal. This original signal is decomposed into approximate and detail as over here. So you have it detail and approximate. This is the first level, right? Then further the approximate, right? Further the approximate is decomposed into second level, approximate and detail. And then in the third level, you can say that the approximate is further decomposed into approximate and the detail. And thus we have the different level of decomposition of the original signal. And thus the original signal representation, we can write it as A1 plus D1. And thus A1 is further decomposed into A2 and D2. And then A2 is further decomposed into A3 plus D3. And thus the you can say the combination of all these coefficients should give you the original signal, which you have it here. Now, next, with this brief introduction to the my presentation, I just want to move on to the implementation of these techniques for islanding detection problem. And here we have the case of a DG system with PV, which consists of PV photovoltaic systems, and then a fuel cell, and as well as the wind system here. And they have their own circuit breakers, and then you have some loads as well. And then this complete combination of these energy resources, power resources, they are connected to the grid to the circuit breaker operation here. So this is the complete, you can say that hybrid DG system operation. Now here this slide shows you what is the approach or the algorithm which we have applied for islanding and power quality disturbance detection using the wavelet transform. So we have the acquisition of the signal, voltage signal. Then we have the negative sequence obtained from the voltage signal. And then we do have the calculation of energy content and standard deviation of the signal. And as I said earlier, that we need to decide a threshold. And thus, if the indices of energy and standard deviation is greater than the threshold, then we refer the event as islanding. Otherwise, we say that some disturbance of related to power quality here. So this is the complete flow chart here. And then we do this continuous monitor form. So that means we have this flow chart run for a finite window length in a continuous form. So, and thus if one window length text signal is analyzed, then we move to the next window length here, right? This is the complete flow chart for discussion. And same way we have used Stockwell transform. So in this case, we obtain the voltage signal, and then but we compute the S matrix here, and we have the calculation of some indices, energy matrix and the standard deviation, and again we decide a threshold, and depending upon the matrix indices matrices greater than the design threshold, we say it's islanding, otherwise event related to the power quality here. So with this part, as you can see here, this is the example where we have the wind system connected to the grid. So as you can see that we have the negative sequence signal variation for voltage signal we have obtained. And then the detection that we applied with the dBs mother wavelet with 4 decomposition levels. So this you can say the variation of the approximate coefficient and the detail coefficient here using the mother wavelet. Next one, This is the case of the discrete mother wavelet, and here we have it by representation for approximate and the detail. And the same way with the use of S transform, the contour representation using S transform is given here, as shown in this figure here. And thus we can see that the contour instant, this contour representation indicates the instant of ion landing here. Same way, even with the use of detail coefficients or the approximates, we can know the instant of ion landing occurrence here in the system. Next one, we have the some noise introduced into the signal, and it is of amount 20 dB. And then the negative sequence variation is shown in this figure. And then you can see here that if you use the wavelet approach, the instant of ion landing event is not reflected in the detail coefficient here. We don't notice in the time instant. We don't do that. We don't have it here, and thus we can say that the wavelet is not able to reliably indicate the instant of ion landing event if the signal consists of noise here. However, if you same way with the Davis mother wavelet, so next one, if you consider the Stockwell transform, the contour representation is independent, because if you refer to the previous slide, if I go back, you can see the contour representation without noise signal, and if I consider the contour representation with the noise signal, it is not affected, and thus the detection island detection that we achieve using the S transform is reliable and accurate here. Similarly, we did some experiment test also, and then here we have the combination of motor and generator set, which is basically the wind generator representation, and then the board represented the synchronization panel with the utility grid from the supply side here. So we have the some load here, and then we have the synchronization switch that is useful for the event to take place. So with this experiment setup, we did some study, and then you can see here
ये
that
क्या
this
बोले
is the waveform which you get it for voltage signal,
कहाँ है
right? And then because we did
आते तो ना
the
किसी को
study as offline analysis, and thus this is the regenerated voltage signal, and the detection that we obtained by wavelet, and then those by S transform is shown here. However, if the signal is superimposed with some noise, then you can see here that the mother wavelet transform has failed to detect the instant. But using the S transform, we can have a reliable detection of signal. And then the case here we have the fuel cell system. So in this case, the negative sequence variation you can see, and then its detection using the wavelet approach and the other mother wavelet approach, and then using the S transform here. So they are perfect in detection for the island event. However, if you have the superimposition of the signal with the noise, then you can see here that the wave rate approach has failed to detect the instant of ion landing here. However, with the use of S transform, we can have the contour representation, and that is the indication of ion landing event for the signal with the noise superimposed. Now, similarly, we did some study for the disturbance for PV system connected to the grid, and you can see here that the variation of negative sequence component, and then detection using the wavelet, and then different mother wavelets, and detection using the S transform here. And when we have the signal, let's say that if you have combination of generation systems. So we have a wind and the fuel cell. So this is the variation of the negative sequence component and the detection using the mother wavelet and using the S transform. So they have been reliable even for these hybrid combinations in the system. And then if you have all the three in combination, then the variation of negative sequence components and detection using the mother wavelets and using the S transform. So that's for even in the hybrid systems, the detection using these techniques, they have been reliable and accurate for landing. Uh, Next case here, I have the detection for fuel cell and PV connected to the grid with three-phase fault uh, afterwards. So that means we have the ion landing, and then we have a three-phase fault, and after the fault is isolated, then we have the ion landing event. And for this situation, the variation of the negative sequence component, and you can see how the coefficients of the wavelet vary. But the representation by S transform indicates that there is some event occurrence in the system, right? But the wavelet does not signify any event occurrence here. However, if you refer to the same, let's say that you have the fault and there is a islanding before fault. Then in that case, in that situation also, so we have the fault. In fact, pre-islanding event here, and then we have the fault followed by fault. So even in this situation, so we have the detection by mother by the wavelet being failed. However, by the S transform, we have the indication about the islanding, and then again by the fault event here. So that means this is the situation. That means you have it as a one event occurrence followed by another event occurrence. So for this situation also, the detection using the S transform has been reliable here. Next one, we refer to some of the other disturbance, and we have the example of a quality signal, and it is of a notch. So we have this negative sequence component of a voltage signal with a notch occurrence, and the detection using the wavelet techniques. You can see here that we have it, and the same way if you use it by S transform, so we have the indication about the noise in the noise present in the signal here. So we have one here and we have another one here. So we have those events, notch events occurrence indicated by these techniques here. Then again, we have the noise for a wind system connected to the grid. So this is the negative sequence component, and then detection using the wavelet, and same way using the S transform, it is reflected here. And if in case you have the signal superimposed with the noise, so you can see that the mother wavelet, it fails to indicate the presence of a noise. However, using the S transform with the counter representation, it indicates the noise occurrence here. Next power quality disturbance, we take an example of a swell occurrence for a wind system connected to the grid. And here we have, you can see that this is the waveform, the original waveform, in normal original waveform. And if there is a swell of, you can say 3 cycles, something. So in that case, detection of the swell using the wavelet approach, and then detection using the S transform, we have it here. However, if the signal is imposed with the noise, then swell is not detected by wavelet here, right? However, we can have perfect indication using the S transform for a noisy signal here for swell occurrence. Similarly, we did some experiment also, and this is the case of a noise for a voltage signal and the regenerated signal and the negative sequence of the voltage signal, and then detection using the wavelet and using the S transform. However, if you consider with the noisy signal, then the detection using the wavelet has failed. However, the performance using the S transform, it remains consistent even with the noisy signal here. Similarly, we have the detection for voltage sag with harmonics introduced. So we have the variation here of voltage signal with swell and harmonics included, and using the wavelet approach and using the S transform. So we can know what are the contour representation for the event here. Next, we move on to this analysis more in depth here. And then we have it, let's say, because you have a DG system and the system characteristics may change, right? So we want to know that whether the algorithm that we have, it will work for detection of islanding or power quality or even islanding fault occurrence if the system parameter, mainly here we consider the grid impedance, the system characteristics change. So we have the verification of the algorithm even for this situation for the system characteristic change here. And thus, now this because of the what is the effect of variation in the grid impedance that is represented that is discussed in the slide. In fact, grid impedance change may have an impact on islanding and detection, power quality detection algorithm. Yeah. Because we have it based on threshold selection, and thus its value, the impedance value, I mean, it may change the time frequency resolution and thereby the performance here, detection performance. It may have an effect. This grid impedance change we have obtained by varying the resistance and inductance of the line, and by the calculation of the performance indexes, that is the energy content and the standard deviation. We have calculated it for each grid impedance, and these numerical values they were determined in fact comparatively higher in the case of S transform. This is for the safe margin for deciding appropriate threshold value. Further, the effect of grid impedance change on detection of other two cases we have analyzed. That is the case of simultaneous islanding event and fault occurrence, and then power quality disturbance. So this is a study we perform. So on this slide, I have it. In fact, the how does the energy indices vary? The energy content and standard deviation vary for the case of islanding for different grid impedance. So we have a wide range of grid impedance as you can see on the x-axis, and how does the energy value and standard deviation vary for this range of grid impedance. It is shown here for the case of island detection, and this is another case here actually. For case 2, in fact we have two different systems, so this is for another system here, and we can see that how does the energy and standard deviation value. So thus, the standard deviation and the energy content, they do not cross the threshold value which we have selected in our design here. Similarly, for the case of we have the study for the in fact of grid impedance for which we consider the simultaneous occurrence of islanding event with three-phase fault. And even for these different kinds of event occurrence, the variation of energy and the standard deviation, they do not cross the threshold that we have considered in the design here. So next, now from here we find here that the algorithms which we had, they were reliable in the detection objective. So, but in some cases we are also interested to classify them because we need to apply some mitigation approach, some mitigation techniques, because we want a improvement in the signal waveform, and thus uh, we have the in fact you can say as another method applied so that we can classify the types of the events here. And for this, we have used one of the technique that is, I hope you are aware of, or maybe it might have been in discussion in another presentation, and it is the modular probabilistic neural network. So this probabilistic neural network, it has different layers. So it has three layers. In fact, most of the neural networks, they have input layer, hidden layer, and the output layer here. And these networks, they use kernel-based approximation functions to calculate the density functions here. And what is the advantage here? Training process is a single stage here, single pass network without having a need for iteration. So as that means because during the iteration we adjust the weights because we want to train it, right? So we do need to have those actually here, and thus the training of this PNN is faster as comparable to the monolithic neural network. You can say the conventional ones. No, in fact, this modular PNN, that means it will have several structures, yeah, and substructures you can say. And this approach is based on how does the brain performs for a given specific task, that is subdividing the tasks into a modular form. And each module will perform the subtasks independently but in parallel to each other. And thus, any complex real-time problem can be divided into subtasks, and however, they can be computationally solved using those subunits, which we call them as modules here. There are advantages here because the architecture is simple, and then each computation, they are independent to each other, and thereby it will be a faster approach with respect to the single or the monolithic structure of the neural network. Here I have some background to the about the topic, about the method. So what is probabilistic neural network? In fact, this is, we have it for classifying the input pattern, because let's say that you have several disturbance, right? Let's say you want to classify sag, swell, moment, interruption, or any other islanding event. So you have some patterns of a signal, right? And we want to classify them. So this, with this approach, with a given pattern of X, we want to have it classified using the Bayesian decision rule. So if you consider that that could be, let's say, some predefined classes. So let's say that you have those signals or those events into different class. So S1 to XK. So this is, that means we know that we have a sag, we have a swell, we have a moment interruption, we have a notch, we have an island. So with these 5 classes, now we can have, that means predefined classes. So these 5 classes can be as a predefined classes here, and then we define a function that is a probability for each class here. So for each class we define a probability function here, and then we give a condition for the pattern with respect to each class here, right? And finally we obtain the probability of the complete pattern, complete input signal. And then next stage we obtain the positive probability of the class with a given X pattern here. So as an example, I can say that, let's say that you have a complete class. You have a five patterns of a signal for corresponding to different events, as I said, sag, swell, moment, interruption, islanding, and so on. So now these classes will have a subset. It will be equal to as subset of k, and then it will have a subset of different class events here. That means the sets of all here, right? And then I can skip this one. And next one is the is what should be the approach, because we want to estimate the probability here, right? So thus for each pattern belonging to a predefined class here, we obtain a function. That means by the probability here, probability for a given class here, right? So this is how we have defined it here. And then using this Persian estimator, so using the equation where you have the 1 by 2 pi, and then m is the dimension, whether you have it as a two-dimensional pattern or multi-dimensional pattern. So based on that, and this is the complete input pattern of data signal, that means for classification which you use here, and which is a exponential function here. And then this we correlate with the Gaussian function with the fx defined here. And then finally, we obtain a network of 4 layers. So we have the input layer, we have some exemplary layers, the pattern layers, which will have the interconnections to the input layer. And then we have, as I said, that it is a submodular form. So we have some more layers here, right? And then finally, the decision layer here. So here for each exemplar layer, this intermediate layer, for this case, we use the radial basis functions nodes, right? And then next one is the class layer, this one, where we have the person estimation. And then the last one, the output layer, which is the decision layer, for which we are interested to know what is the class of the event here. So with this, in fact, some of the, you can say the features, so the characteristics of the technique. This techniques is based on the Bayesian rule, and this approach is much faster because, as I said, that you don't need to have the training, and thereby the learning is also much faster. And it will the performance is guaranteed to approach the Bayesian optimal decision surface. However, this will depend upon the probability density function here. Then these state nodes for time, they may not be good for large training samples. Yeah, that is one disadvantage you can hear. Then probability density function, it has to be represented as a smooth and a continuous form. This is required here. Then another approach that we have is the use of support vector machines. You must have heard of it. And this is another technique which is much more powerful, mainly for classification objective, right? And this approach overcomes the limitation of the neural networks, and mainly in terms of we don't have any convergence issue or the overlearning, and then again we don't need to have what should be the size or what should be the network here. We don't need to do that part. In fact, support vector machines, they can be useful for both binary as well as for multi-class classification. So, and thus we can have it for different examples here. Right. So, and in our part of the discussion, we have it is used for fault classification or maybe classification for power quality disturbance. With this support vector machine, the input pattern, that means the feature sets, they can be mapped into dimensional space, because let's say if you want to have a multi-class, so in that case we need to represent in a high dimensional space, and thus each hyperplane can be obtained for each classes here. And this approach gives you a generalized property, right, as comparable to, and thus that means the performance will be reliable. And how and training is based on sequential minimize techniques, so we don't have any sophisticated approach being applied for that, for the support vector machine training. Yeah. With a flow chart for the classification, that means the suppression, we have the signal from the PCC, that means pointer copper coupling for the voltage signal. Then we extract the negative sequence signal, we obtain the S transform, and then we, as I said, that S transform was a way of was more accurate or reliable in detection, so we have used the S transform, we have used the features calculated from the S transform only. And then we calculate some indices, energy and standard deviation, and then based on the threshold we say that whether it is islanding or oil quality disturbance. So with this we have some statistical features, let's say energy of magnitude contour corresponding to the maximum magnitude of each column of the S matrix, then standard deviation of the magnitude contour corresponding to the maximum magnitude of each column of the S matrix, the energy of phase contour, standard deviation of the phase contour, mean value of magnitude and the phase, then skewness of magnitude and the phase contour, and cortices of magnitude and the phase contour. So these are the features which we have used for the classification of these events here. So as you can see here, this is just the approximate classification. So we have the EMC, SMC, and then SDMC. In fact, this is all refers to EMC, SDMC, EPC, and all this part here. So on the three-dimensional plot, we have those representation, and we have all these events here: sag, swell, notch, momentary interruption, and islanding contour representation. But this is an approximate classification here. And similarly, with these statistical features, they are representation of the features for these events. They are represented, but it's not exact one, right? Uh, then again, with the combination of different features, we have their representation of the for the different classes, as you can see. But after having used we have used uh, modular probabilistic neural network and the support vector machine techniques here. And then with those techniques, we are able to now, depending upon how many features you use for classification in the techniques here. So we have used 3 features, 5 features, 7, and altogether 10 features here. So how does the classification performance? That means the accuracy will vary here. So we have it for normal signal, we have it for sag, swell, notch, and momentary interruption here. So thus, this is the complete classification accuracy here for different combinations of the features. Same way, here you can see how does the performance will vary if we have the different combination of the features. So altogether, it is much higher here. Then, as you can see here, that this is in the tabular form we have represented. So for the case of modular probabilistic neural network, we have an overall efficiency of 97.4% for classification of these events. And if in case the signal consists of some noise, then if performance classification performance is 92% something, and if it is some 30 dB noise, then obviously it is clear that if performance will improve. Then the same way with 40 dB, definitely 96.4, it will much higher here. Then again, with the use of support vector machine, because in this case we need to decide what should be the parameter for support vector machines. So we have the C parameter, and with that, how did the performance will vary. So we have shown the graph here, the variation of the performance here with the selection of the parameter here, right? And this is the case again, support vector with the noise free condition. Now here we have selected a sigma function here. How does the classification vary? And then with the selection of different kernel function in the support vector machine, whether you consider radial basis function or the polynomial kernel. So we have the performance indicated here. And same way we did it some more analysis with the noise changes. So you can see that the performance is something 98 points or 97 point something or 94 or 99% here. And then the with the as support vector machine techniques, you can see what is the contour representation. So let's say that you want to classify the SAG with the other classes. So you have the SAG event, and if you want to classify SAG with respect to other type of events, so it is indicated here, right? The contour representation. So you can see that all the events, all the features corresponding to the SAG, they are within here. However, other class events, they are here. Similarly, noise versus all other classes, you can see that noise plus symbol. So we have it somewhere here, some of them, right? And then other classes here. Similarly, momentary interruption against all other classes. So momentary interruption, this one. So all of the events related to the momentary interruption with the classification boundary are represented here. And same way with the swell with other classes against all other classes. So you have swell, this symbol, and then we have it most of the events here located on this part here. And then because sometimes we are also interested to classify between sag and swell and notch and momentary interruption. So this is the classification boundary to classify this swell event here and then sag event here. Same way between notch and momentary interruption. So we have it for notch and the momentary interruption with this classification boundary indicated here. Then again, we did some more study. Let's say that you have a variation in the wind speed, solar radiation, load, and so on. So we have all these classes corresponding to these different operating situations actually. You have the sag because of this, you have the swell because of these operating conditions. And that's also we have considered in our study. And you can see that with the use of neural network and support vector machine, and then again the advanced version of support vector machine that we call it as least square. So we can see that the performance using the least square is 96%, and with the use of traditional conventional support vector machine 94%. However, neural network it is something 93% here. With the noise introduced, we have some impact here, right? Then further, we did some more study, and then you can say that classification of the different classes C1, C2, and C3 for wind system. So we have corresponding to the different situations of operating condition. So we have all these classes here, C1, all C1, C2, and C3. These have been classified, and then same way for the swell. For C4, C5, and C5, they have been classified distinctly using the support vector machine here. In fact, it is the least square support vector machine here. Then we did some more study for the different classes with the different techniques. And you can see that what is the overall percentage in the performance using between the techniques here without noise and then with noise here. And then last one, in fact, just to have a demonstration that how does the technique perform. So with the we have referred a receiver operating characteristic using the LSSVM. So between C1 and C4. So this is somewhat closer to Unity here. So and that's that means the technique has performed well here. It reflects here because here we have the sensitivity, and on this side we have the false positive rate here. So with this, I like to end, and I think we are near about the time. So, and these are the references that I have, and these are the references which were used in my presentation here. And if you are more interested, these references can be referred by you, right? And I welcome if you have some more queries. Thank you.
Any
Hello, sir.
queries?
Hello,
Yes,
sir.
ma'am. Please continue, ma'am.
Sir, I'm V. Jayashree, madam, from Maharashtra. Sir, S transform has performed very well for detecting island faults. And in that, do we have to set any parameters for this S transform in order to detect that island phenomena?
Yeah, we have to, as I said, that parameters related to the S transform that is important here. So, because in the case of S transform, we don't have to do it actually, right? We don't have because in the case if you refer to the mother wavelets, right? So because if you consider the wavelets, so here you have to decide what should be your mother function, and then what should be your decomposition level. You have to
Yeah,
that is the choice you have to make actually,
right,
right?
sir, right.
But in the case of S transform, you don't have to do anything that what should be the function, all that part, all those parameters, they are not required as in the case of S transform. That I can say here.
Okay, sir.
This is what you wanted to have.
Okay, sir. And another thing,
Yeah,
only ion detection is done by S transform. Then other sag, notch, these are
yeah,
done by them, sir.
yeah. In our problem actually, we have used S transform for islanding, right?
Ah, ah,
And then we have also used S transform for power quality disturbance detection also. We have
okay,
it. I think if you go back in some of my, uh, if I refer this one, can you see miss this slide here?
yes, sir.
Yeah. So this is the case of a swell. And
Okay,
I think this is for a noisy signal. So we find the counter representation using the S transform here. We have it. So we have applied S transform for islanding and as well as for power quality signal. And I think earlier slide, this is the case where we have it for swell, and then this is the case for a notch detection
okay.
using the S transform. So we have applied these techniques even for power quality. Yeah, we have done that.
That means S transform detection can do the detection for all types of, including island detection.
Yeah, in our case we have found it. In our case we have found it. Yes, I can say.
Okay, sir. Thank you, thank you.
But I cannot generalize this. Maybe if, because if you change your system and then some other things, then maybe S transform may not work. That is
Okay,
possible. Because I have some more study. So we found that S transform has not a clear indication about the event occurrence. And that's why we move to some other techniques. So we have that also. So, but in this part, I have discussed S transform only.
okay,
So because that this is the work we did it, I think in 2012 and 13. But if you refer some, maybe I think in the later part, in the afternoon session, I have the use of EMD techniques. So EMD techniques, they have been more useful for the islanding event actually. So there
okay,
we have not used S transform.
okay, okay. Thank you.
Any more?
Any more questions from participant? Okay, I hope there is no more questions. So thank you very much, sir, for delivering informative and wonderful talk on the topic of disturbance detection in the distributed generation system. Thank you very much, sir, for your valuable time from your busy schedule for this lecture. And again, we will resume at 2:30 for our next session. And topic is real-time evolving disturbance detection and classification in distributed generation system. Thank you.
So now we can log out, Dr. Vijay, right?
Yes, sir. Again, we will resume at 2:30.
Okay, fine. Thank you.
Thank you,
Thank
sir.
you.